Connect the ground cable to a ground connector first, then the phase connectors using hotline tools. They'll be removed in reverse order. Phase connector first, then the ground connector. Proper bonding and grounding is a necessary requirement for electrical systems and equipment. Bonding and grounding is used to create a low impedance path to cause protective devices to operate and clear a circuit during a ground fault condition. Bonding and grounding also minimizes the risk of electrical shock and equipment damage. In this segment of our Electrical Safety for Industrial Facilities series, we will identify general requirements for bonding and grounding of electrical installations. As we all know, equipment continues to function even if the ground becomes disconnected. If a ground fault occurs on ungrounded equipment, the equipment enclosure becomes energized. This occurs because ungrounded equipment does not provide a path back to the system to cause the overcurrent protection device to clear the fault. This is why it is so important that the grounding conductor be continuous and is maintained intact. There are two types of grounds or ground systems: service grounds and equipment grounds. Each has a specific purpose. A service ground is the grounding of one conductor of the system to a ground electrode. Service grounds limit voltage surges from lightning strikes and other causes that may impose a high voltage condition on the system. Equipment grounds bond together all the metal parts of a conductor path. This includes electrical raceways, boxes, and enclosures on all non-current carrying metal parts. Equipment grounds prevent objectionable potential above ground on non-current carrying metal parts. It also provides a low impedance path for ground faults and must be permanent and continuous. The grounded conductor It is well recognized that insulated tools and equipment are essential for doing energized work. It is just as essential for using personal protective grounds when doing de-energized work. Personal protective grounds provide the primary protection in the event a circuit under repair inadvertently becomes energized. In this program, we will identify the function of personal protective grounds, describe the basic design requirements for personal protective grounds, and demonstrate techniques for installing and removing personal protective grounds. When maintenance or other type of work is performed on or near de-energized equipment, the only way to assure that the equipment will remain de-energized is to short circuit and ground the system. In industrial and commercial electrical systems, grounding of current-carrying components can be difficult and sometimes impossible to do. The primary purpose of personal protective grounding is to prevent accidental death or injury to workers from electric shock by minimizing the magnitude and duration of the hazard. Static charges can build up on an isolated circuit or equipment due to airflow, friction, dry conditions, and dust. The direct current voltage adds to any alternating current voltage that may be present. A single ground connection will immediately drain off this charge and bring the conductor to ground potential. Discharges associated with static charges are relatively small and last a fraction of a second. People are more likely to be injured from the reaction to the shock than by the shock itself. Capacitively coupled voltages exist whenever two or more conductive surfaces are separated by insulation. If one or more of the surfaces is energized, a 60 Hz voltage will be induced between the surfaces. An example of this might be a substation bus conductor and earth. The substation acts as the bus conductor's conductive surface, and the air acts as the insulator. Steady-state charging currents will flow due to this capacitate effect. Electromagnetically coupled voltages exist when a de-energized, non-grounded conductor closely parallels an energized conductor. When this occurs, static, capacitively coupled, and electromagnetically coupled voltages all exist together in varying magnitudes on each phase conductor. Grounding one end of the de-energized conductor discharges the static and capacitively coupled voltages. The electromagnetically induced voltage, however, cannot be completely discharged even if grounds are placed on both ends. The reason why this is so is because the energized conductor acts as the primary winding of a transformer, and the de-energized conductor acts as the secondary winding, creating a transformer with a 1-to-1 ratio. A low value of mutual inductance is created. Possibility of operating the wrong breaker. Operating the wrong breaker affects normal plant operations in unexpected ways. Equipment may stop, then restart without warning. Results can range from minor inconveniences to injury or fatalities. If the wrong circuit breaker is operated, report it immediately. Do not re-energize the breaker. Always open rack in and rack out circuit breaker switches with doors closed. Whenever possible, operate breakers from remote control switches. If remote control switches are not available, stand to one side and turn your face away from the breaker when opening or closing the breaker. The next piece of electrical equipment that carries possible hazards is the fuse. Fuses are generally safe and reliable circuit protective devices when they are properly rated for the application. A fuse has 3 ratings that must be considered for proper operation: the voltage rating, the ampere rating, and interrupting rating. The voltage rating of a fuse must be at least equal to the applied circuit voltage. It can be higher, but never lower than the circuit voltage. Ampere rating. Every fuse has a continuous current rating. When this rating is exceeded due to overload or because the fuse was not rated properly, the fuse will blow and clear the circuit. Underrating the fuse size usually does not create a hazard to personnel, but does cause unwanted delays in the operation of the equipment. The interrupting rating of a fuse is often overlooked. Interrupting ratings are generally printed in small print on the side of a fuse and must be properly applied. A misapplied fuse with an incorrect interrupting rating could explode.